Hi, in this video, I'm looking at this problem here, where we've got a person landing a 6 kilogram drone, which was initially hovering 20 meters above the ground. To commence landing, they reduced the thrust to 42 newtons upwards, and there was a breeze blowing on the drone horizontally with a force of 15 newtons. And we want to calculate what was the acceleration of the drone, how long did it take to reach the ground, and how fast was it traveling when it reached the ground. So this problem is a problem around multiple forces acting on a body. So if we have our body, we've got our drone here, then we've got 42 newtons of thrust pushing upwards on it. And we've got that wind pushing horizontally, and I'm just going to define it as going to the right horizontally. So we've got 15 newtons of wind, but we also have gravity. So we've also got the gravity pulling the drone down, which is going to be a force of 6 kilograms times gravity of 9.81, or 9.8, which gives us 58.8 newtons due to gravity. Well, that's our weight of the drone. So we've got these three forces acting on our drone, and we want to find out what is the overall resultant force acting on this drone. So basically, we want to know what is the resultant force, which is pushing it most likely in this direction because we've got more weight than we do thrust, and we've got the wind pulling it this way. So our resultant force is going to come from adding all of these forces up. So if I think in my horizontal direction, I've got 15 newtons horizontally, so I've got 15I. Vertically, I've got 42 newtons vertically upwards, but then I've also got that minus 58.8 newtons downwards. So we've got negative in the j direction. And so then our resultant force is going to, if I add all these up, become 15I minus 16.8 j newtons. So that's the overall force acting on our drone. So then to get acceleration, we're going to use Newton's second law, F equals ma. Force equals mass times acceleration. Or if I rearrange this, acceleration is going to be force divided by our mass. Now our force in this case is going to be our overall resultant force. So I'm going to have our 15I minus 16.8 j force. And then I'm going to divide that by the mass of our drone. And the mass of our drone was 6 kilograms. So I'm going to multiply that by 1 on 6. And so then if I multiply that 1 on 6 in, we're going to get acceleration as a vector. Because in this case, I started with the force vector. So I'm going to get acceleration vector. And that's going to give us 2.5 in the horizontal direction minus 2.8 in the vertical direction meters per second per second. So that gives us the acceleration vector. But if we want the overall acceleration, then we're going to need to convert this so that way we have just pure acceleration linearly. So then if I want to do that, well, that means that I need to know the magnitude and, of course, angle of our acceleration. So we can get the magnitude of our acceleration, which is going to be done by Pythagoras, the square root of 2.5 squared plus negative 2.8 squared. And that gives us an acceleration of 3.75 meters per second. And our angle is going to be given by inverse tan of our vertical over our horizontal. And if we work that out, That gives us an angle of negative 48.24 degrees. So that means that our answer for part A that we've just worked out gives us that the drone is accelerating at 3.75 meters per second at an angle of 48.24 degrees below the horizontal, or as an angle of depression. So that's our answer for part A, is that the drone is accelerating at 3.75 meters per second at an angle of 47.24 degrees below the horizontal. So now we've got our acceleration, we can look at the time taken for the drone to reach the ground. Now, if we think about what's going to happen, we're told that our drone is initially 20 meters above the ground. So if we think about redrawing a new diagram, we've got our drone and we've got the ground, and there's a distance there of 20 meters. And we've got our acceleration for that drone being it's accelerating at 2.5 meters per second horizontally and downwards at 2.8 meters per second. Now, the horizontal motion is not going to define the length of time it takes to reach the ground. It's going to be our vertical acceleration only. Because our horizontal is just going to keep pushing it sideways, it's not going to change how much this vertical distance is changing. So that means that we just need to really look at our vertical acceleration and just use that to then calculate how long it's going to take for the drone to reach the ground. So we, for part B, are just going to take the vertical acceleration of negative 2.8 meters per second and work from that. So now we need to get to equations or something that's going to tell us about how long it's taking to travel distances. So that means I've got to go from acceleration to displacement. So our acceleration is currently known, and we also know that acceleration is the change of velocity over time. So that means that I've got dv dt equals our acceleration vertically of negative 2.8 meters per second. And I can use this differential equation that dv equals negative 2.8 dt and then integrate to get to that my velocity is negative 2.8 times time plus some initial velocity, which I'm just going to call v naught. But what is my v naught? If I go back to my problem, I'm told that it's hovering. Hovering means that it's stationary, or at least for us, close enough to approximately stationary. So that means that we can say that at t equals 0, velocity equals 0. And if I think about substituting 0 in for this, I've got 0 equals negative 2.8 times 0, which means that therefore our v naught equals 0. So that means that our velocity is just going to be negative 2.8 times time. But I need displacement. Now, to get to displacement, that means I've got to know that velocity is the change of displacement over time. So that means our displacement over time is defined by negative 2.8 t. And so that means I can get ds equals negative 2.8 t dt. And so now, playing around with this differential equation, if I now integrate, I get that my displacement is going to be given to me by negative 2.8 t squared on 2 plus some initial displacement. Now our drone is hovering 20 meters above the ground. So that means that we have our initial displacement. we know that at t equals 0, displacement equals 20. And so if I substitute in 20 here equals 0 for time here, this term here is going to cancel out, and I'll have my initial displacement equals 20 meters. So that means that my displacement formula equation is now negative 1.4 times time squared plus an initial 20 meters. And so now I just want to solve this equation, and that means I need to know when is my displacement equal to 0. So I want to know at what time does my displacement equal 0? Because if my displacement is 0, it means I'm on the ground because I'm only looking vertically. So I've got 0 equals negative 1.4 t squared plus 20. And so now if I go and solve this, I've got negative 20 equals negative 1.4 t squared. T squared equals 20 divided by 1.4. So t is going to be plus or minus the square root of this 20 on 1.4. Now, negative time makes no sense in this because we're just going from now onwards. So we can ignore the negative and just say that our time is 3.78 seconds. So the drone takes 3.78 seconds, or almost 4 seconds, to reach the ground. So now just doing the last part, what was the velocity of the drone when it reached the ground? Well, because of our effort of doing our displacement having to go through velocity, I got this formula that velocity equals negative 2.8 t. Now, that was only our vertical velocity, but if I think about what's happening overall, I've still got my horizontal component that I need to consider for my velocity. But if I look at what happened to get this velocity equation, I started off with my vertical acceleration, and my velocity became that acceleration times time. So for doing part C, I've got that velocity equals acceleration times time. And in part A, we got our overall magnitude of our velocity to be 3.75. So I want to use here that my overall velocity was my acceleration was 3.75, and then substitute in my time it took to get to the ground, which was 3.78. So that means that the drone was traveling at 14.17 meters per second when it hit the ground. So in this case, because I want overall velocity, because the drone's going to head down this way and hit the ground, I need to consider that horizontal component, because everything is involved when I'm talking velocity. We considered all forces when considering acceleration, so we need to also consider all forces when we're considering velocity. Because the horizontal component had no impact on the time taken to reach the ground, I could ignore that horizontal component for part B, but that's because my main thing I cared about was just that vertical travel distance. But because I'm wanting overall, I need to consider everything within my velocity problem. So there we go. If we've got multiple forces acting on a body causing it to move, we can find our resultant force by adding them all up. We can then get to equations of motion by using F equals ma, Newton's second law, to then get acceleration. And then from acceleration, we can answer things like velocity and displacement questions. Depending on what the problem is, depends on whether we need to take into account all of that motion, or whether we just want to focus on one particular direction at a time. But it all comes down to us using our differential equations and integration techniques and just thinking through the problem that we have.